In this video we'll take a look at stationary points. So at a stationary point or a turning point, the slope of the tangent is 0. So to find a stationary point we set the first derivative to equal 0, dy dx equals 0, and then we'll solve to find the x values of the stationary points. We use the second derivative to test the nature of the stationary points. So if the second derivative is greater than 0, then the point we found is a minimum. If the second derivative is less than 0, then the point we have found is a maximum. If the second derivative equals 0, we have a point of inflection. And we'll do a couple of examples just to show this. We're given a cubic equation, y equals x cubed minus 6x squared plus 9x plus 1. And on the sketch we can see the points A and B. A and B are both stationary points or turning points. The value of dy dx, the slope of the tangent at A and at B equals 0. So to find these stationary points we would first find dy dx and then solve for x. So the first derivative of dy dx, we have dy dx equals 3x squared minus 12x plus 9. And we must set this to 0. We set it to 0. We have a quadratic equation now. I can factor the 3 out of the quadratic equation. So we have 3 on x squared minus 4x plus 3. And we can find solutions to this quadratic equation by factorising. So we'll have x minus 1 and x minus 3 for our factors. So we get two values of x. X could be equal to positive 1 and x could be equal to 3. So one of these is the x-coordinate of the maximum and one is the x-coordinate of the minimum point. Now we want to find the coordinates, so we'll just take the x value of each of these points and sub it back into the curve to find the value of y. When x equals 1, we have 1 cubed minus 6 times 1 squared plus 9 times 1 plus 1. So the coordinates of the first turning point are 1, 5. So that equals, the y value equals 5, giving us the coordinates 1, 5. We do the same with the x equals 3. So y equals 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. So the coordinates where x equals 3, the y value is 1, and the coordinates will be 3, 1. Now we have a sketch of this curve, so it's quite easy to see that the point A is 1, 5 and the point B is 3, 1. But if we didn't have a sketch, we will use the second derivative test to determine which is the maximum point and which is the minimum point. So we have our dy dx equals 3x squared minus 12x plus 9. And we're going to get the second derivative and then apply the test to determine the nature of these stationary points. So the second derivative, d2y dx squared equals 6x minus 12. So when x is equal to 1, we sub in 1, we will have 6 times 1 minus 12. The second derivative, d2y dx squared, equals 6 minus 12, which is negative 6. Now this is less than 0. So we have shown that the point 1, 5 is a maximum. And we can see that from the curve. The point A is the turning point, which is the local maximum on this cubic equation. And we test again when x equals 3. We sub in 3. We have the second derivative d2y dx squared when x equals 3 is 18 minus 12 is positive 6. So we say this is greater than 0. Therefore, the point 3, 1 is a local maximum. We have also on the curve the point C, and point C is the point of inflection. So this is the point where the curve is changing direction. You can see as the curve is rising, you get to the maximum A. The curve is convex up until the point C, and then there's a direction change at the point C where the curve becomes concave. So it becomes like from a hill to a spoon shape. And this is the point of inflection, and we use the second derivative to find the point of inflection by setting d2y dx squared, set it to 0. d2y dx squared equals 6x minus 12. We set that to 0 and solve for x. So x equals positive 12 over 6 is 2. So the x coordinate at 2 has a y coordinate of, we'll sub in the 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1, and that will give us the point of inflection, which happens when y equals 3. So the point 2, 3 is our point of inflection. In the second example, find the coordinates of the stationary points and state their nature. And we're given the curve y equals 2x cubed plus 9x squared plus 2. So to first find the coordinates, we'll get the first derivative, dy dx, and set it to 0. So the first derivative, dy dx, is 6x squared plus 18x. We set that to 0. Now we have a quadratic equation, and this quadratic equation we can factor. We first of all factor out the 6 on x squared plus 3x. And then if we further factor that, we have 6 on x plus 3 equals 0. So we have two possible values for x equals 0 or x equals negative 3. So we need to find the coordinates of the stationary point. So the x value of the first stationary point happens when x is 0. So when x is 0, y equals 2 times 0 cubed plus 9 times 0 e plus 2, so y equals 2. So the first stationary point has coordinates 0, 2. The second stationary point we find by subbing in x equals minus 3. Minus 3 cubed plus 9 times minus 3 squared plus 2. And that, when we calculate that, we get positive 29. So the second stationary point has coordinates negative 3, 29. And we do need to state their nature, so we'll use the second derivative test, d2y dx squared. So the second derivative, we will differentiate the first derivative again, so 2 times 6 is 12, x plus 18. And we test this first when x is 0. The second derivative becomes 0 plus 18 equals 18. This is a positive value, it's greater than 0, so the point 0, 2 is a local, it's a local minimum. So when we test the second derivative when x equals negative 3, we sub that into the second derivative, so we've got 12 times negative 3 plus 18, and that gives us negative 18. Negative 18 is less than 0, so the point minus 3, 29, is a local maximum. So that's all for this video. Thank you for watching.